Hi there. Today we're going to be starting Unit 5, and the first thing we're going to be doing is evaluating nth roots and using rational exponents. One thing that we've used in the past are perfect squares. Perfect squares are numbers whose square roots are integers. So those are numbers like 1, 4, 9, 16, etc. And we've used perfect squares when we were dealing with square roots of things. We were dealing with perfect squares when we were factoring the difference of two squares, etc. We've also talked about perfect cubes. Those are numbers whose cube roots are integers. So those are numbers like 1, 8, 27, 64, etc. And we became more familiar with perfect cubes when we were factoring the sum and difference of two cubes, and we used the cube roots in those. But today we're going to be looking at roots, but not just square roots and cube roots, but any types of roots. And so let's define the nth root of a. For an integer n greater than 1, if b to the n equals a, then b is an nth root of a. So what that means that if 4 cubed is 64, then that means that 4 is a cube root of 64. Okay, so that's what an nth root of a means. So if something to a power gives you a number, it's that root. I'm also going to talk to you today about the index of a radical. We have the index of a radical. An nth root of a is written like this, where we're going to use the square root symbol, but we're going to put this here, and this is called the index of the radical. Okay, when we see a square root on its own, that's the same as like having an index of 2, but usually we don't write that, you know what I mean, because the square root is so popular. So we won't write this, but the square root is really equal to this. This is really what we're going to use for square roots. But when we have something other than a square root, we're going to put that as what's called the index. Okay. So let's talk about real nth roots of a. If n is an even integer, which means we're going to have an even index, that means that we're going to be taking an even root. What we have to do is we have to consider this idea of plus or minus. Okay. If we had something like b to the fourth equals negative 16, so our a value is negative, what we would want to do is take the fourth root, and anytime we insert an even root, an even index, we need that plus or minus. Now the thing is that we can't take the even root of a negative, so that's why we would have no real roots if we have the even root of a negative. Now, if a is 0, so if b to the fourth equals 0, once again, what we would want to do is, because it's an even root, we're going to take plus or minus, and we're going to have 4 as the index. Well, the fourth root of 0 is 0, and there's no difference between plus or minus 0, so that's just going to be b equals 0. Now, if our a value is positive, if we have something like b to the fourth equals positive 16, once again, what we'll do is we'll take the fourth root of 16, since it's even, we have a plus or minus, and we would want to find what the fourth root of 16 is. This is where we're going to come back to our table of powers that we've been working on. And if we want to take a fourth root, that means that we're going to look where there are these fourth powers, And notice that I see that 16 is the same as 2 to the fourth power, which means that the fourth root of 16 is 2. So we're going to be using this backwards to help us find roots. And so again, since the fourth root of 16 is 2, and we inserted that even root, our answer would be that b is plus or minus 2. I forgot to box the 0, okay? Now, the thing is that if we have an odd root, so if n is an odd integer, so if we have an odd index, there is no plus or minus, okay? So we are going to, for example, use 8. So if like b cubed equals -8, then what I would do is I would want to take just the cube root of 8. Now, there isn't something that we could multiply n times to get a negative, but you can multiply something an odd number of times to get a negative. And so if we look at the cube roots, the cube root of 8 would be 2. And when we think about it, the cube root of -8 would be -2. So notice that if it's odd, we can take the odd root, or the root of a negative. Once again, if it's 0, to get rid of the cube, we would just take the cube root, and the cube root of 0 is just 0. And if we are trying to take the cube root eventually of a positive number, again, only one positive number would work there, and that would be a +2. So going forward, anytime that you have any sort of an even root, we're going to insert a plus or minus. But if it's an odd root, there's always just one possibility. Okay? So another thing we're going to focus on today is this idea of rational exponents, okay? And when we have rational exponents, that means that we're going to have an exponent basically that's a fraction. And when we think back to the properties of exponents, we know that if we raise a power to a power, we're multiplying them together. So the way that we're going to attack these rational exponents today is we're going to say, all right, if we have a raised to the m over n, then that's like a to the 1 over n to the mth. And that idea that a to the 1 over n is going to be the same as the nth root of a. So this idea that a to the 1 over n is equal to the nth root of a is crucial as we deal with these rational exponents. Okay? Essentially what's happening is that when you have the rational exponents, the denominator of your rational exponent becomes the index of the radical. Okay, that's the relationship that we're looking at today, that the denominator of your exponent is going to become the index of your radical. Now, if we have a negative exponent, we know that negative exponents have to move to the denominator, and then we can do the same thing. We can think about a to the m over n as a to the 1 over n to the m, which is really the nth root of a to the m. And so since it's in the denominator, 1 over the nth root of a to the m. So here's just a little sample of that. If we had -125 to the -2/3, then I'm going to start by getting rid of the negative exponent. I'm going to have 1 over negative 125 2/3. And now to help me evaluate, I'm going to use this idea that the denominator of the exponent becomes the index of the radical. So the negative 125 is going to be the radicand. The denominator of my exponent is 3. That becomes the index of the radical. And then I'm going to raise that to the second power. So now I want to take the cube root of negative 125. If I don't know what that is off the top of my head, I can go to the power chart and look under cube 25, and I can see that the root of positive 125 is going to be 5. Remember, cube roots, odd roots can be negative. So the cube root of negative 125 is going to be negative 5, and negative 5 squared is still going to be positive 25. So our answer is 1/25. Okay. So let's practice evaluating this. And I know that we talked about up here that if there's an even root to have a plus or minus, that's when you insert like into an equation. So when we have the expressions like we have in example 1, we do not put plus and minuses on our answer here, okay? We're legit evaluating the expressions. There's just going to be one answer. The plus or minus really is only when we have equations, you guys, okay? So let's do the steps that we did in the last sample in this example 1. So this wants us to evaluate without using a calculator. But you can use the power chart and you'll be able to use that on quizzes and stuff like that. I'm just going to make a note up here, no plus or minus in expressions. Just because I've seen students do that a lot and I just want to make sure that it's clear, like that's not a thing. If there was a plus or minus in front of it already, yes, but notice we're just evaluating these. We don't put the plus or minus in, okay? So let's look at 64 to the negative 1/6. Well, the first issue is that this is a negative exponent. So let's rewrite it as 1/64 to the 1/6. Let's then rewrite this to the 1/6 using an index. So 64 is our radicand. And now the denominator of our exponent is the index of the radical. And going forward, I probably wouldn't put it to the first because we know that anything to the first is just itself, but I'm just kind of making sure you understand what we would do with the numerator. Okay? So now I would want to take the 6th root of 64. And if I'm not sure what that is, I can go to my power chart. And since I'm looking for the 6th root, I'm going to look at n to the 6th. And I see that the 6th root of 64 would be 2. So that's going to be 1/2 to the first, which is just 1/2. And that's what 64 to the negative 1/6 is. What about 9 to the 3/2? Well, this is a positive exponent, so we're good. So we're going to rewrite this as with 9 underneath. And remember that the denominator becomes the index of the radical. I'm not going to write a 2 though, because we usually don't write 2 as an index. I'm going to leave that as the square root of 9, and then I'm going to cube it. Okay, so yes, there is a little 2 that's in here, but we don't write it. Okay, it's kind of silly. It's like writing 1x or like writing x to the first. Like you just don't do it, right? So we don't write 2 as the index. So anyway, so let's take the square root of 9, and the square root of 9 is 3. And now I have, well, you can put that in parentheses here, okay? So the square root of 9 is 3, and then 3 cubed is 27. And so that's what 9 to the 3/2 is. If we had 16 to the negative 1/4, again, I have a negative exponent. I'm going to rewrite that as 1 over 16 to the 1/4. And now I'm going to rewrite here. I know that this is going to be like the 4th root of 16 and then to the 1st. Again, if we're not sure what the 4th root of 16 is, we can look at n to the 4th. We go to 16. We see that the 4th root is going to be 2. And 2 to the 1st is just 2. So this answer is 1/2 as well. And then letter D, 36 to the 3/2. Again, because my denominator is 2, that's going to be like the square root of 36. I'm not going to put 2 as the index though. And then cubed. So the square root of 36 is 6. And 6 cubed, hopefully we know, is 216. If not, again, you can use the power chart the regular way. You can take 6 cubed to find that that's going to be your 216. Okay, so I'd like you guys to pause the video and try these questions with that same process. Okay, so just take a minute and pause the video to see if you can do it on your own. Okay, really pause. Okay, see you in a second. Okay, I hope you paused. But these are the answers that hopefully you came up with in the your turn question. Number 1 is 1/16, 2 is 1, and 3 should be 9. Okay, if you have any questions, make sure you message me. Okay, now if we try that in this example 2, what we would be thinking about is we would be thinking about doing the cube root of 10. And if I look on my power chart, I see that there aren't any integers that are cube roots of 10. And so notice that's why this is asking us to do that with a calculator. And even though when we evaluate things by hand, I think it's easier to think about the radicals. When we evaluate things in the calculator, it's going to be easier for us to do with the rational exponents. So remember that our exponents are going to be that caret key. Okay, so I'll just make a little note here, reminding you guys of that, that we have the caret key that we use for exponents. And that's on any calculator. Sometimes on the scientific calculators, it's like this y to the x or x to the y button, but on most of them, it's the caret key. So again, this is fine, but this is what I'm going to put in the calculator. And I'm just legit going to take 10, and I'm going to press the caret key. And then if you have this here, then you can just put 1/3, and that'll be your answer. If you have the old form and you have this, you need to put the 1/3 in parentheses. If you don't, what it's going to do is it's going to raise it to the first power and then divide it by 3. Do you see how that's different? So if you have what's called the classic format, make sure that you're putting the exponent in parentheses like this, okay? So I'll just here kind of put this in parentheses just in case, all right? But again, if you have the math print type where when you push the caret key, it elevates it for you, you don't need to have the parentheses there, okay? So make sure you're familiar with whatever calculator you have. The same is true for some of the scientific calculators. Some of the scientific calculators, you need parentheses. Some of them elevate it for you. So make sure that you're comfortable with the calculator that you're using. Oh, this wants us to round to the nearest hundredth, which is 2 decimal places. Okay. So we look at the 3rd decimal place, which is 4. That tells us to keep that decimal of 5 in front. So this is about 2.15. I deliberately am putting that approximately equal to show that I am rounding and that 2.15 is not the exact answer, but just an approximation. If we have something like 21 to the negative 1/4, I'm just going to type it in like that. If I'm using my calculator will do that, putting it into the denominator for me. So I'm not even going to rewrite with positive exponents when I can use the calculator. So if I do 21 to the 1/4, notice the third decimal is a 7, which tells me to bump this guy up. So that's going to be about 0.47. Okay. Now in letters C and D, notice that they have an index, and you can do that on the graphing calculator. Like, I know you can, but I really feel that in these specific questions, that these are going to be easier to do with the exponents. Because it really is kind of this like clunky way that you have to do an index in the graphing calculator. So let's rewrite this as an exponent. So again, 13 would be our base. Our index is 6, so that would be the denominator of our fraction. And it's not being raised to anything, so that's just, it means that it's to the first. So that's what I'm going to put in my calculator for this one. I'm going to put in 13 to the 1/6. And that's going to give me about 1.53. So much easier than doing the 6th root in the calculator, I promise, okay? Now let's rewrite this. 80 is our radicand, so 80 is going to be our base. 4 is our index, so that's our denominator. And -2 is the exponent, that's going to go in the numerator. So I'm just going to put 80 to the -2/4, and that's approximately 0.11, okay? So if it's in the calculator, not really a lot of work to show, but I would still kind of write what you're typing in the calculator for the ones that are the radicals, okay? Okay, so next, let's talk about solving equations. To solve an equation, x to the n equals a, what we can do is take the nth root of both sides. And again, when you take the nth root of both sides, that is the same as raising it to the 1/n power. Okay. So in letter A, this says 2x to the 6th equals 1,458. And we want to take the roots. But before that, we have to make sure that your power is isolated. So I wouldn't start 3a by taking the 6th root. I need to isolate the x to the 6th first, which means what would I do to both sides? Divide by 2. So I would end up with x to the 6th equals, what is that, 729? Okay, so x to the 6th equals 729. And now I want to take the 6th root of both sides. So I'm going to take the 6th root, but notice that this was an even root. And when we insert an even root into a problem, we need to have a plus or minus that we put in front. Okay, so what I see then is that the 6th root of x to the 6th is going to be x. And now that was a 7. I want to try to find the 6th root of 729. So I look under n to the 6th, and I see that the 6th root of 729 would be 3. I had that plus or minus because of the even root. My answer would be plus or minus 3. So x equals plus or minus 3. Okay. In letter B, I have the quantity x plus 8 to the fourth equals 2. Notice that this is already isolated. So I can start by taking, since I'm raising it to the fourth, I'm going to take the fourth root of each side. And because I'm inserting an even root, I need to make sure that I have a plus or minus that's in front there. So I'm going to have x plus 8 equals plus or minus. And if I look on my sheet, I see that 2 isn't on here. So right now, I'm just going to leave this as the fourth root of 2. Okay. And I want to isolate x. So I have x equals -8 plus or minus the fourth root of 2. Okay. And this is the exact answer. Okay. Which I like the exact answer, okay? Like on a test, that's probably what I would ask you to write it as and leave it as. But this did ask us to round to the nearest hundredth. So let's think about what this really means. So in the calculator then, this is going to be like -8 plus the fourth root of 2. And in the calculator, it might be easier for us to write that as a rational exponent. So it's 2 to the 1/4. And then we're going to take -8 minus 2 to the 1/4. Okay. And so we can just type that in. So I can take -8 plus 2 to the 1/4, and then -8 minus 2 to the 1/4. And then I get my answers. So this first one, the 0 keeps the 1. So I have -6.81. Here the 9 bumps the 8 up to a 9. So -9.19. And those would be my two approximate answers if it's asking us to round to the nearest hundredth. So again, I personally prefer this, the exact answer, but if I think the questions ask you to round to the nearest hundredth, if that's the case in the homework, then that's how you would do that. Okay. Letter C. X cubed minus 9 equals 31. Well, again, I need to isolate this first. So I'm going to add 9 to get that x cubed equals 40. Now that that's isolated, I'm going to take the cube root. And again, this is an odd root. So that means no plus or minus. So that legit just means that x equals the cube root of 40. No plus or minus because it's an odd root, an odd index. I look and I see that 40 is not a perfect cube. So that means, again, this is the exact answer, which I like. Okay, but I always have to look at the direction. Since the direction said to round to the nearest hundredth, that's going to be like 40 to the 1/3. So I'll take 40 to the 1/3, and that 9 bumps this 9 up. So really it's like the 19 is bumping up to a, oh, sorry. I was rounding to the nearest thousandth in stats. We're rounding to the nearest hundredth, my bad. So I look, this 9 bumps that 1 up to a 2. So that's going to be 3.42. Okay. Sorry, hundredth is just 2 decimal places, my bad. Okay. Okay. Then there are a couple story problems, but they're not bad, you guys. Like they give you, you're basically just putting things in, okay? They like give you something, you put it in, and you go to town. So example 4 says the population P of a certain animal species after T months can be modeled by P equals C times 1.21 to the T over 3, where C is the initial population. Find the population after 19 months if the initial population was 75. All right. Well, this is after T months. and this is looking after 19 months. So this is telling me that T is 19. Okay. And then it's also telling us that C is the initial population and that the initial population was 75. So that's saying that C is 75. So then you guys just legit put those in here. So this is saying P equals, we don't know what P is, right? So P equals C, we said that was 75, times 1.21 to the T, which we now know is 19 over 3. So all you do is put that in your calculator, legit, okay? Like not hard. So 75 times 1.21 raised to the 19 over 3. Remember, if you have the old kind of calculators, make sure that you put 19 over 3 in parentheses. And that gives me about 250.82. I know we had been rounding to the nearest hundredth. And I know technically we don't have that 0.82 of an animal quite yet. I'm going to give it the benefit of the doubt. I'm just going to use traditional rounding rules and say that this is going to be about 251 animals. And again, because of the approximate, then you could have that argument with people about that. Because someone might say, oh, well, it's not quite to the 251st animal. You said, well, it's about. Okay. Yeah, there are different schools of thought for rounding. Anyway, all right, example 5. Volume of a beach ball. I bet you guys did something like this one in geometry. The volume of a beach ball can be approximated using the model V equals 4/3 pi r cubed, where r is the radius of the ball in inches. It wants us to estimate the radius of the ball if the volume is 382 cubic inches. So this is saying the volume is 382 cubic inches. So that's what we're going to put in for V. So legit, we'll say that 382 is going to go in for V equals 4/3 pi r cubed. Now remember that we can't take any roots until we isolate the power. And so the power means I'm just going to isolate this r cubed. So one of the things I have to get rid of is this 4/3. So what's something I could do to get rid of the 4/3? Hopefully you're thinking about multiplying by the reciprocal. So I'm going to multiply by 3/4. Okay, that cancels these. And that gives me on this side pi r cubed. And dividing by 4 usually isn't too bad. If I take 3/4 times 382, that gives me 286.5. So a terminating decimal, I like that. Okay, now we still have to isolate this r cubed. So what we want to do now is get rid of this pi. Well, we were multiplying by pi, so let's divide by pi. So I'm going to keep this in the calculator, and now I'm going to divide by pi. Don't use 3.14, use the pi key on your calculator, wherever that is. And I see that I get about 91.196 is equal to r cubed. Now that this is isolated, I can get rid of the cube by taking the cube root. Do we need a plus or minus? No, this is an odd root. There's no plus or minus. So I'm just going to take the cube root of this, which is really like raising it to the 1/3. Okay. So I'm going to just take the answer and raise it to the 1/3. And what I find is that R is about 4.5. Are we rounding to the nearest hundredth still? It doesn't say. we should, if we're doing the nearest hundredth, I know it's annoying to have the 0 there, but it's appropriate. So R is going to be about 4.50 inches. Okay, and that's that. So that is a little bit about the radicals and the rational exponents. Again, this is your buddy. You're going to want to keep this guy around, and you can use that on your homework to help. You'll be able to use it on quizzes and tests, etc. Okay, so that's a little bit about the radicals and the rational exponents. Okay, have a great day, guys.